Today, we're going to talk about DeMoivre's theorem, which gives you an easy way to raise a complex number to a power in polar form. Basically, if we have r cosine theta plus I sine theta, and then we want to raise this to some power n. So we're going to have r to the n, that's self-explanatory, and then we're going to distribute these into the angle. So we're going to have cosine n theta plus I sine n theta. When you wanted to do this normally, so if you wanted to do, say, 2 plus I squared, you could use the perfect square formula, or basically is generally just like, expanding it like this, and then you're going to FOIL, and so we're going to get 4 plus 2i plus 2i, and then minus 1, so you're going to get 3 plus 4i. And it's much faster when you have it in polar form using DeMoivre's theorem. So we're going to do a little proof of this, proof by induction. We're going to do it for the integers. We're going to say that we're going to actually ignore the radius for this, since it's kind of self-explanatory. You just distribute in, but we're going to take that cosine theta plus I sine theta to the n is equal to cosine n theta plus sine n theta. And so yeah, we're just going to do it for an inductive proof for integers. So our first case is going to be n is equal to 0. By our proposition, this should be that cosine theta plus I sine theta to the 0 should be equal to cosine 0 theta plus I sine 0 theta. Now I'm just going to look at the left hand side here. We already know that this is going to evaluate to 1 plus 0i, which is just equal to 1. And for the left hand side here, we know that all numbers to the power of 0 should be equal to 1. So what we're going to get is basic, so this side is just going to be equal to 1. And so yeah, left side equals the right side. We're good with this case. Now what we're going to do is assume that the case with n equals to s, that's just some arbitrary variable. We're going to assume that this case is true by what we've seen here, what we've proposed. Okay. So then we're going to try the case n equals s plus 1. Okay. So we're going to have cosine theta plus I sine theta to the s plus 1 should be equal to cosine s plus 1 theta plus I sine s plus 1 theta. Okay, so, and once again, we're going to look the left hand side. So we can, by exponent laws, we can split these into, so cosine theta plus I sine theta, split this to cosine theta plus I sine theta to the s times itself, cosine theta plus I sine theta. Now with this, again, we're going to assume that the case n equals s is true. So we're going to have cosine s theta plus I sine s theta, and then yeah, just times cosine theta plus I sine theta normal. And now we're going to expand this. So we're going to have cosine theta times cosine of s theta plus I times cosine theta sine of s theta. Then carry here, we're going to have I sine theta cosine s theta, and then minus sine theta sine s theta. Okay, now I'm going to rearrange this into its real and imaginary part, or basically factor. So we're going to have cosine theta cosine s theta minus sine theta sine s theta plus I, this is all factored out, cosine theta sine of s theta plus sine theta cosine s theta. So here, this is our real part, and this is our imaginary part right here. Now, you might notice that we can apply some trigonometric identities to simplify this, mainly the angle sum identity for both cosine and then sine. So what we're going to have here is, so first cosine of theta plus s theta, and then plus I, and this is sine of theta plus s theta. And then this we can factor further within the angles here. We can factor further to get exactly, we can factor out a theta, so we get cosine s plus 1 theta plus I sine s plus 1 theta. So this has been proven nicely. The left hand side is equal to right hand side, so this works for all positive integers here we actually considered, but let's also test the negative integers. So say we just have, for a case, n is equal to -1, okay? So then with this, we're going to have that cosine theta plus I sine theta, the -1, should be equal to, is going to figure out cosine negative theta plus I sine of negative theta. And again, I'm going to consider left-hand side. We know that this is going to go, since cosine is even and then sine is odd, we're going to have cosine of theta, minus I sine of theta. This negative is going to be factored out here. So, looking at the left-hand side, we can rewrite this as 1 over the reciprocal cosine theta plus I sine theta. And then we're going to want to multiply by the conjugate here. Yeah, cosine theta minus I sine theta over itself. This way we can get rid of a complex denominator. So now we're going to have cosine theta minus I sine theta over, so these guys are going to get multiplied by a difference of squares. So what we're going to get a real portion. We're going to get cosine squared theta plus sine squared theta. And by the Pythagorean identity, you know that this is just going to be 1 over here. So we get that this also works for negative numbers. All you have to do is just factor out the negative here due to cosine being even. It's going to stay there, and then sine is odd, so it's just going to come out. Now, you have been thinking, hold on, can't we just do a simpler proof using exponential form? And yes, that is true. If we have e to the I theta to the n, this is just going to be equal to, cosine theta plus I sine theta to the n. Then we're going to have e to the I theta n, so we're going to have cosine n theta plus I sine n theta. However, with this case, we are considering all other numbers, including like the rest of the real numbers, and also like basically the complex numbers if we had a complex power or a fractional power basically. However, with those cases, there are some exceptions. You're not going to get an exact definite value, and we're going to see why here. Let's say we are going to have theta equals 0. So we're going to have theta equals 0 and n is equal to 1 over 2. Okay. So then we're going to have cosine of 1 over 2 times 0 plus I sine of 1 over 2 times 0. This is just going to be, again, it's just equal to cosine 0 plus I sine 0. Cosine 0, that's just 1. Sine 0, that's just 0, so you're going to have 1 plus 0i, which is simply just 1. Okay. However, if we know about the periodicity of complex numbers, you change the angle to 2 pi, then we're still going to get, this is still going to be 1. Okay, so it's still going to be square root of 1 basically. So let's try that out with, now we're going to have, yeah, so theta is equal to 2 pi, which is still in polar form, that's still 1, okay? N is equal to 1 over 2. So we're going to have cosine 1 over 2 times 2 pi plus I sine 1 over 2 times 2 pi. And so this, we're actually going to see these guys are going to cancel out. And so what we're going to get is cosine pi plus I sine pi. Now, cosine of pi, that's going to be -1. Sine of pi, that's still 0. So our final answer is going to be -1 plus 0i, which is just -1. So here, you can see that we have multiple values. There's not a single definite value. And the reason that this comes about is that fractional exponents here with DeMoivre's theorem, it kind of goes around the essence of roots of unity, which is basically you're going to have, because you could either have -1 squared can be 1, and so can +1, and so this kind of goes with the fact that if we have x is equal to root of 1, because that's what we're looking at here, square root of 1, we can square both sides. X squared is equal to 1, so we're going to get x squared minus 1 is equal to 0. And when you factor this, we're going to get x plus 1 and x minus 1 is equal to 0. And so on the complex plane, what we're basically going to have is these two opposing points here. So yeah, so this here is 1 and this is -1. And so this basically you're going to have these values for n is equal to 0 and 1, basically from 0 to whatever the root is -1. Okay, so this is going to be your x1 here and your x2, and this also follows through with say this is the square root of unity if you have the cube roots of unity. So we're still gonna have 1 over here, but then the other two, again, once you bring it back to the other side and then factor using difference of cubes, you're going to get over here is going to be 1 over 2 plus root 1 over 2 plus root 3 over 2i, and then here it's going to be 1 over 2 minus root 3 over 2i, and that will be the same here if you bring it to n equals 1 over 3. So this goes around with the fact that you're going to have these separate solutions and the fundamental theorem of algebra, one real, it's going to be 2 complex, and yeah, so that's a thing that we have to note, that z of n is multi-valued for non-integer values of n. Okay, but then what if we want to raise it to a complex power? let's say again we're going to do for theta is equal to 0. So this is just going to be again 1 to the I basically. Theta is equal to 0, n is equal to I. We're going to do this. This is just basically 1 to the I. And again, considering periodicity, we have it in exponential form here. We're going to have e to the I, and it's going to be theta plus 2 pi n. And so here, when you don't have it to a complex power, you are going to have periodic answers. You can keep on increasing whatever n is, but you're going to get the same like number of finite answers. But here, complex powers, some stuff is going to cancel out, and you're actually going to get infinite solutions from this. So if we're going to have this, we're basically going to have, I'm going to go in the negative direction too, but basically we're going to have e to the I negative 4 pi to the I e to the I negative 2 pi negative 2 pi I. Then we're going to have e to the I 0 I, now in the positive direction, e to the I 2 pi I, and e to the I 4 pi I, and so on and so forth. So these i's, when they're going to be multiplied here, going to cancel to give us, or yeah, I squared, that's going to be negative 1. So what we're going to have here is e to the 4 pi, e to the 2 pi, this one is just I to the 0, e to the 0, that's just 1, e to the negative 2 pi, e to the negative 4 pi, and so on and so forth. And these are real results here. These are just going to keep on going. They're infinite. Okay. Basically, it's just going to be of the form e to the 2 pi n or let's actually use k here. This is different than the exponent that we were using, e to the 2 pi k, for k is an integer. Okay. So yes, DeMoivre's theorem does work for every number from every set. You just have to know that there are special cases for the rest of the real numbers and also complex numbers when you raise them to those powers. I hope you enjoyed this video. Hope it was very informative. This is a very useful theorem here. Please click like and subscribe, and I will see you in the next video.